Hello viewers, welcome to the channel Amazing Civil Engineering Studies. Time to enter the world of civil engineering. Here we will learn about different concepts related to civil engineering. Please subscribe to the channel and press the bell icon for more new updates. In today's video we are going to discuss about flow in open channels. The flow of liquid through a canal with a free surface is defined as open channel flow. This free surface of the liquid is subjected to atmospheric pressure. Hence, open channel flow can also be defined as the flow of liquid through a passage at atmospheric pressure. The flow in an open channel takes place due to gravity that is achieved by providing a bed slope. Introduction. Open channel flow involves the flows of a liquid in a channel or conduit that is not completely filled. There exists a free surface between the flowing fluid, usually water, and fluid above it, usually the atmosphere. The main deriving force is the fluid weight. Gravity forces the fluid to flow downhill. Under steady, fully developed flow conditions, the component if the weight force in the direction of flow is balanced by the equal and opposite shear force between the fluid and the channel surface. There can be no pressure force driving the fluid through the channel or conduit. For steady, fully developed channel flow, the pressure distribution within the fluid is merely hydrostatic. Examples of open channel flow: the natural drainage of water through the numerous creek and river systems. The flow of rainwater in the gutters of our houses. The flow in canals, drainage ditches, sewers, and gutters along roads. The flow of small rivulets, and sheets of water across fields or parking lots. The flow in the chutes of water rides. Types of open channels: prismatic and non-prismatic channels. A canal in which the cross-sectional shape, size, and the bottom slope are constant over long stretches is termed as prismatic channel. Most of the man-made or artificial channels are prismatic channels. The rectangular, trapezoidal C-figure, triangular and half-circular are commonly used shapes in man-made channels. All natural channels generally have varying cross-section and consequently are non-prismatic. Rigid and mobile boundary channels. Rigid channels are those in which the boundary or cross-section is not deformable. The shape and roughness magnitudes are not functions of flow parameters. The lined channels and non-erodible unlined AP channels are rigid channels. In rigid channels, the flow velocity and shear stress distribution are such that no major scouring, erosion or deposition takes place in the channel, and the channel geometry and roughness are essentially constant with respect to time. Channels are classified as mobile channels when the boundary of the channel is mobile and flow carries considerable amounts of sediment through suspension and is in contact with the bed. In the mobile channel, depth of flow, bed width, longitudinal slope of channel may undergo changes with space and time depending on type of flow. The resistance to flow, quantity of sediment transported and channel geometry all depend on interaction of flow with channel boundaries. The flow of liquid through the open channel can be of several types like steady and unsteady flow, laminar or turbulent flow, or uniform or non-uniform flow, and finally subcritical, critical, and supercritical flow. Types of flow in open channels: steady and unsteady flow, uniform flow and non-uniform flow, laminar flow and turbulent flow, critical, subcritical, and supercritical flow. Steady and unsteady flow in an open channel flow: if the flow parameters such as depth of flow, the velocity of flow and the rate of flow at a particular point on the fluid do not change with respect to time, then it is called a steady flow. If v is the velocity of the fluid, ch is the rate of flow and d is the depth of flow, then for a steady flow, dv dt equals 0, dq/dt equals 0, dy dt equals 0. N is at any point on the open channel flow. The flow parameters like depth of flow, the velocity of flow and rate of flow do change their value with respect to time, then it is called as an unsteady flow. It is hence given by dv dt dq/dt and dy dt not equal to 0. Uniform flow and non-uniform flow. The flow in the channel is said to be uniform if, for a given length of the channel, the velocity of flow, the depth of flow remains constant. I.e. dy ds equals 0, dv ds equals 0. In a non-uniform flow, the flow parameters like velocity, depth of flow, etc. do not remain constant for a given length of the channel. dy ds and dv ds not equal to 0. The non-uniform flow can be again defined as rapidly varying flow, r.v.f, and gradually varied flow, g.v.f. In the case of rapidly varying flow, r.v.f, the depth of flow rapidly changes over a smaller length of the channel. It rises up suddenly for a short length and settles back. While in a gradually varied flow, g.v.f, the depth of flow changes gradually over a longer length of the channel. Rapidly varying flows, RVF, the flow depth changes considerably over a relatively short distance dy dx1. Gradually varying flows, GVF. The flow depth changes slowly with distance dy dx1. Laminar flow and turbulent flow. Laminar and turbulent flow in open channel flow is defined based on the Reynolds number, Re. The Reynolds number is given by the relation. If the Reynolds number Re is less than 500 or 600, then the flow is called laminar flow. If the Reynolds number is more than 2000, then the flow is said to be turbulent. A flow that has Reynolds number between 500 and 2000 is said to be in the transition state. Critical, subcritical, and supercritical flow. The open channel flow is categorized as critical or subcritical or supercritical based on the Froude number Fe. Froude number is given by the relation. Open channel flow is subcritical if the Froude number is less than 1. Subcritical open channel flow is also defined as tranquil or streaming flow. An open channel flow with a Froude number equal to 1 is acritical flow. And supercritical flow in open channel has a Froude number greater than 1. A supercritical flow is also termed as rapid flow or torrential flow or shooting flow. Discharge through open channel by Chezy's formula. Consider uniform flow of water in a channel as shown in figure below. As the flow is uniform, it means the velocity, depth of flow and area of flow will be constant for a given length of the channel. Consider sections 1-1 and 2-2. Let L equals length of channel, A equals area of flow of water, I equals slope of the bed, V equals mean velocity of flow of water, P equals wetted perimeter of the cross-section, F equals frictional resistance per unit velocity per unit area. The weight of water between sections 1-1 and 2-2. W equals specific weight of water. A volume of water equals W times A times L. Component of along direction of flow equals W times sin I equals W times A times L sin I. Equation 1. Frictional resistance against motion of water equals F times surface area times velocity, N. The value of NIS found experimentally equal to 2A and D. Surface area equals P times L. Frictional resistance against motion equals F times P times L times V2. Equation 2. The forces acting on the water between sections 1-1 and 2-2 are component of weight of water along the direction of flow, friction resistance against flow of water, pressure force at section 1-1, pressure force at section 2-2. As the depths of water at the sections 1-1 and 2-2 are the same, the pressure forces on these two sections are same and acting in the opposite direction. Hence they cancel each other. In case of uniform flow, the velocity of flow is constant for the given length of the channel. Hence there is no acceleration acting on the water. Hence the resultant force acting in the direction of flow must be zero. Resolving all forces in the direction of flow, we get W times A times L times sin IF times P times L times V2 equals 0, or U times A times L times sin I equals F times P times L times V2. V2 equals W times A times L times sin IF times P times L equals WF times AP times sin. Equation 3. A/P equals M, where Miss hydraulic mean depth or hydraulic radius, C equals V, WF. C equals Chezy's constant. Substituting the values of A/P and V, WF, in equation 3, we get V equals CVM times sin I. For small values of I, discharge, V equals CVM times I. Q equals area x velocity equals A times V. Equals AX CVM times I. Numerical based on Chezy's formula. Find the velocity of flow and rate of flow of water through a rectangular channel of 6 mWid and 3 mDEP, when it is running full. The channel is having bed slope as 1 in 2000. Take Chezy's constant C equals 55. Solution. Given width of rectangular channel B equals 6 meter, depth of channel D equals 3 meter, area A equals 6x3 equals 18 m2. Bed slope I equals 1 in 2000 equals 1/2000. Chezy's constant C equals 55. Perimeter P equals B plus 2D equals 6 plus 2x3 equals 12 meter. Hydraulic mean depth A/P equals 18/12 equals 1.5 meter. Velocity of flow is given by V equals C.Vmz equals 55 V 1.5x, January 2000, equals 1.506 meters second. Rate of flow, Q equals Vx area equals Vxa equals 1.506 x 18 equals 27.108 m3/second. Determination of Chezy's constant by empirical formula. The Chezy's constant C is a dimensionless quantity which can be calculated by three formulas, namely Bazin formula, Gangulet-Cutter formula, Manning's formula. Bazin formula. This formula is developed in MKS units. The Bazin formula is given by Bazin formula. K equals Bazin's constant, m equals hydraulic mean depth or hydraulic radius. The Bazin's constant is dependent on the roughness of the channel surface. More the roughness of the surface, higher is the value of Bazin's constant. Values of K in the Bazin-S formula. S no. Nature of channel inside surface. Value of K. 1. Smooth cemented or planed wood. 0.112. Brick or concrete or unplanned wood. 0.213. Rubble masonry or ashlar or pour brick work. 0.834. Earthen channel of very good surface. 1.545. Earthen channel of ordinary surface. 2.366. Earthen channel of rough surface. 3.17. Gangulet cutter formula. This formula is developed in MKS units as where N equals roughness coefficient, which is known as cutter's constant, whose value for different surfaces are given in table below. I equals slope of the bed. M equals hydraulic mean depth. The slope of the bed is given by I and the hydraulic mean depth or hydraulic radius is given by M. Value of N in the Gangulet cutter formula. S no. Nature of channel inside surface. Value of N. 1. Very smooth surface of glass, plastic, or brass. 0.0102. Smooth surface of concrete. 0.0123. Rubble masonry or pour brick work. 0.0174. Earthen channels neatly excavated. 0.0185. Earthen channels of ordinary surface. 0.0276. Earthen channels of rough surface. 0.0307. Natural streams, clean and straight. 0.0308. Natural streams with weeds, duples etc. 0.075 to 0.15. Manning's formula. The value of K according to this formula is given as where M equals hydraulic mean depth, N equals Manning's constant, which is having same value as Cutter's constant for the normal range of slope and hydraulic mean depth. The values of N are given in above table. Thank you for watching. Numerical will be discussed in another video of flow in open channel. For now, please subscribe, like, share and do not forget to press bell icon.